In the last lecture, we were talking about Joule-Thomson expansion, and we got this nice curve that represents isenthalpic porous plug experiments. So the locus of all the points representing the equilibrium state with the same enthalpy is this curve. So let's talk a little bit more about that. So in the previous lecture we talked about a single experiment, or a series of experiments I should say, in which we keep the pressure and temperature on this side constant, and then we change the pressure on this side, the pressure on this side, and then measure the temperature for each of the pressures. Okay, so the pressure and temperature on the higher pressure side, on the left side, are represented by P1 and T1, and the pressure and temperature on the low pressure region, or on the right side, is represented by P2 and T2. Okay, so again we are keeping P1 and T1 constant, and then we are changing P2 on the lower pressure region, and we record the temperature on the right side. So if we do the same experiment, but now if we change the temperature on the high pressure region, okay, so we change this temperature, and for each of the temperatures we do the exact same experiments, then what we will get, so we'll get a graph for each of the temperatures. Okay, so we have this temperature on the low pressure region and pressure on the low pressure region, or on the right side of this porous plug device, and for each of the temperatures on the left side of the high pressure region we get an isenthalpic curve. So for, let's say, for a particular temperature we get this isenthalpic curve, call that T1, okay, at temperature T1, and then let's call that T11. 1 is for the temperature on the left side, and this 1 is for one particular temperature, and we get for another temperature on the left side we get another isenthalpic curve. Okay, do the same experiment, but now the temperature is changed. Let's call that T12, and if we change the temperature we get another curve. Okay. If we do another experiment with different temperature we get another isenthalpic curve, 1, 2, 3, 4, and then another curve, okay, we get a bunch of curves like that. So we get this family of curves corresponding to different values of enthalpy. Okay, so for each of these curves we also have a particular enthalpy. So all the points on this curve have same enthalpy. So let's call that H. We call it H1. Here we have enthalpy H2, enthalpy H3, H4, H5, H6, okay, and so on. So now if the temperature on the left side, which is T1, is not too high, then the curves, or isenthalpy curves, will pass through a maxima or a maximum, called inversion point. We talked about this last time a little bit. So inversion point is the point where the cooling process converts to the heating process. So below the inversion temperature or inversion point, you see the cooling effect, and after the inversion point you see the heating effect. Okay, so some gases like hydrogen and helium have low temperature for inversion. So usually in those gases you have to cool the gas to low temperature, pretty low temperature, to see the cooling effect. So okay, so at inversion point what we see is this ratio, or this slope, which is slope of T with respect to P at constant H. Okay, so slope of each curve where the slope would be 0. Okay, so that's the inversion point. Inversion point is where this slope is 0. Okay, now if I connect all the points where the slope is 0 and connect all those points, then I get this curve. Okay, this curve is the locus of all the points where this is 0, okay, or the slope of the curves are 0, and this curve is called inversion curve. So the locus of all the inversion points is called the inversion curve. Okay, and if we see the inversion curve, we clearly see the the boundary between this left region and the right region. Okay, and what do you know about the left region? So left region is the region where you see the cooling effect, and this right region is the region where you see the heating effect. So the gas shows cooling effect in the region left of the inversion curve. And the gas shows heating effect in the region right of the inversion curve. And exactly on the inversion curve you don't see any change in temperature. Okay, you don't see heating or cooling effect. Sometimes we also say the region on the left is inner region. It's inside the inversion curve, and this region is also sometimes called outer region because it's outside the inversion curve. So if you remember in Joule experiment, not this one but the other Joule experiment, where we showed that the internal energy is only the function of temperature. So in that we showed du dV at constant temperature is 0 for ideal gas. Okay, so in the same way we can also show in this case, in case of Joule-Thomson experiment, dH dPT is constant or is 0, okay, or H is constant. We can show that. So we can express this. We cannot measure this directly in the experiment, so we need to express this in terms of the measurable quantities. So we can write this as partial h partial p t using the cyclic chain rule, partial p partial t at constant h partial t partial h at constant p is equal to -1. So partial h partial p at constant t is equal to -1 over dp dt at constant h dt dh at constant p. So partial h partial p at constant temperature is equal to negative. So we know that this thing is the reciprocal of this is Cp. So Cp is partial h partial, so partial h partial T at constant pressure is specific capacity at constant pressure. So we can write this as partial T partial P at constant h, just taking the reciprocal of that and then moving the things up. So this one also could be flipped and then it will go up. So partial h partial T constant P, so minus this thing is Cp, and that's partial T partial P at constant h. And for the ideal gas, we can show that this thing is 0. Okay, and with that I can write partial h partial p at constant t is 0. Heat engines and Carnot cycle. So let's first define what is heat engine. So a heat engine is a system that receives an input of heat at higher temperature, and it does some mechanical work and it gives off the rest of the heat at lower temperature. Okay, so we can define it as a system that receives an input, call that Q2 at higher temperature, let's also include input heat because it's heat that is the thing that is received by the system or the heat engine, and does mechanical work and let's denote the mechanical work by W and gives off the rest, call it Q1 at a lower temperature. Okay, so let's denote higher temperature by T2 and lower temperature by T1. So before I draw the schematics for heat engine, let me draw two cases and see which one is possible and which one is not. So let's say we have a system denoted by M, and we do some work on the system and we input work W, which is being totally converted to heat, and it is dumped to the surrounding. Okay, so here the work is completely converted to heat. Okay, this is case 1, and case 2 is we have a system, let's call that M. So we extract some heat from higher temperature region. Usually we call this as source of heat or reservoir. This is heat reservoir. So extracted heat Q, and then got work out of the heat. Okay, got work from the system. So heat is completely converted to work in this case. So this one is possible. You can completely convert your work to heat. However, this is not possible. You cannot convert heat completely to work without giving off some of its heat to the lower temperature region, which we call sink. Okay? So that means we need to modify this to a working system or a working machine. So the way to modify that is by using the schematics as shown. Okay, so we have a system M, we have this heat reservoir at higher temperature, call that the temperature T2, and then we have sink, call that T1, which is at lower temperature. So we extract heat from higher temperature region. Let's call the heat amount of heat is Q2. Okay, so this is heat absorbed, and do some work. Okay, so we get some work from the system. So this is work done by the system. So we supply heat Q2 to the system, and then we get heat work W out of from the system, or work W is done by the system, and then we dump rest of the heat to the lower temperature region, which we call sink. Okay, so this heat dumped is, let's call Q1. So this is heat given off. So this is the schematics that actually works. So this is modification of, let's call this B, including a cold temperature sink, or cold temperature you can also call reservoir. And here T1 is less than T2. Okay, so this one does not work. So the main aim of using a heat engine is to get some work, and to get work we need to have a low temperature reservoir in addition to this heat reservoir. Okay. And what is the efficiency of the heat engine? Okay. In other words, how much work you can get out of the heat you that supply. So that efficiency of an heat engine is defined as, it is denoted by Greek letter eta. It is defined as output work over input heat. Okay. So output work is W, and input heat is Q2 in this case. Okay. So we can also write this in terms of absolute sign. So W is absolute work and Q2 is absolute work. Now we know from first law of thermodynamics, heat supplied is equal to work done plus change in internal energy, and heat engines are usually cyclical, work in cyclical process. Okay, so it starts from some initial state and then goes to some different processes, and then eventually it goes back again to the same initial state. Okay, it's a cyclical process. So that means the internal energy in one complete cycle would be same, okay, or there is no change in internal energy for a complete cycle in a heat engine. So that means we can make it 0, so that will give us Q is equal to W. Okay. So here the total heat involved is Q1 plus Q2, that is equal to W. Okay. So we can write this using the sign convention. Okay, here we didn't use the sign convention, so the sign convention is hidden inside the symbol, but if I want to use the sign convention, then Q2 is positive. Okay, so this thing is modulus or absolute sign, absolute value, and because Q2 is heat entering the system, so this is positive, and Q1 is heat leaving the system, so that is negative, that is equal to work. Okay, in this case work is positive because work is done by the system. When the work is done by system, it is positive. So again, the convention that we use for the sign of the heat and work is W by system is positive, W done by or on the system is negative, Q in is positive, and Q out is negative. So using this, we can write the efficiency as work is Q2 minus Q1 over Q2, that is equal to 1 minus Q1 over Q2. Okay. So efficiency of a heat engine is 1 minus Q1 over Q2. Or if I want to write this in symbolic form without incorporating the sign, then I can write this as Q1 over Q2. So here the sign notion is incorporated in the symbol. Okay. Now let's talk about Carnot cycle. So Carnot cycle is first proposed by Sadi Carnot, which comprises of 4 steps in a heat engine, and Carnot cycle is a reversible process. Okay, and in Carnot cycle the working substance is ideal gas. So it's a 4-step reversible process, and in which the working substance is an ideal gas. Because we are using the ideal gas, so Carnot cycle is an ideal cycle. Okay, so in Carnot cycle we get the maximum possible efficiency. So that's how Carnot designed this cycle, okay, to get the maximum possible efficiency. So the 4 steps involved in Carnot cycle are: the first one is isothermal expansion. The second one is adiabatic expansion. Third one is isothermal compression. And fourth one is adiabatic compression. So let's look at the diagram for all these steps. So in the beginning we use this cylinder with some gas enclosed by this piston. Okay, so what we do is we put the system on some heat source. Okay, so this is put over some heat source which is at temperature T2. Okay, so the heat enters the system and it expands isothermally. So we'll maintain the temperature of the system as T2 in this process, and then we allow the gas to expand. Okay, and then this is source. So there is heat Q2 entering the system, and then we remove the system from this heat source and then put it over some insulated surface. Okay, so here is the insulated surface. So that means there is no heat entering the system or coming out of the system. So it's adiabatic process, and we allow it to expand. Okay, so the starting temperature is T2, but as we allow it to expand, its temperature decreases. Okay, so it goes from temperature T2 to some other temperature. Let's call that T1. So this is insulated surface. And then in the third step we remove this from the insulated surface and then put it on some conducting surface. Okay, something like a metal plate or something. So here is a conducting surface, and now the heat will escape from the system to the conducting surface. That will allow the gas to contract or compress. So there would be compression of the gas as the heat escapes out of the system. So then the temperature would be here. From here to here the temperature would change to T1, but here we'll allow the heat to escape in such a way that the temperature remains constant. Okay, so this is an isothermal process. So here we are going through an isothermal compression. Here we are going through adiabatic expansion. The gas is expanding. Here also there is isothermal expansion. Here it's compression. And then in the final step, we remove the system from this conducting surface and put it over some insulated surface, just like here. So we'll put this on an insulated surface. Okay, so there is no heat exchange in this step. So again, this is insulated surface. Okay. Now the temperature here will start with T1 and then it'll increase due to the compression, and it goes back to temperature T2. Okay. And then we'll go back again to the same step here, so initial state. So we'll allow it to compress by removing changing the temperature. Okay, and then the temperature will go back to T2 again. Okay, so this will go back to that step again. So it's a complete cycle, and in this 4-step cycle, what we see here is there is heat Q2 entering the system here. So since the heat is entering the system, so that's Q2 is greater than 0 here, and work is done by the system here. So that means work, let's call that W2, is greater than 0. Here there is no heat involved, so Q is 0, and work is done by the system, so work is greater than 0. Let's call that W prime. Here heat leaves the system, so that means Q1 is less than 0, and work is done on the system because it's compressing, so W1 is less than 0. Here Q is 0, there is no heat involved, and W, let's call that the prime is less than 0 because it's compressing, so work is done on the system. Okay. Now we can represent this whole process in a PV diagram. So we have a graph of P versus V. So to begin with, we have this state, okay, defined by PV, call that state A. So we go from state A to state B. So this is called that state A, state B, state C, and state D. Okay. So we go from state A to state B. This is isothermal expansion, and it's at temperature T2, and then from B to C it's adiabatic expansion, and we know that the adiabatic curve is steeper than the isothermal curve, okay, from our previous discussion. So just a reminder, in isothermal process, the equation of state is PV is equal to constant. That means P is inversely proportional to V, whereas in case of adiabatic process, PV gamma is constant. That means P is inversely proportional to 1 over V gamma. So this, because of this gamma is greater than 1, so this thing is greater than V. That means this goes off faster than this one. If this is the isothermal curve, then for the adiabatic curve it would be steeper. Okay? That's why here we have this adiabatic curve steeper than the isothermal curve. This is adiabatic expansion. And during the isothermal expansion, heat Q2 enters the system, and during the adiabatic expansion there is no heat involved. And then from C to D, there is isothermal compression. By the way, from B to C, the temperature drops from T1 to T2. Okay? And then there is this isothermal compression where there is no change in temperature, but the volume changes, okay, from C to D. And during this isothermal compression, heat Q1 is given off to the sink, and then finally we go from D to A, which is adiabatic compression. Okay, so this one is isothermal compression. So start from point A and then you go back to point A again. So this is a cyclical process. So the total work done during this single cycle is given by a single Carnot cycle is W is, by definition, it's PdV, integral of PdV, and W is, we have 4 pieces of work here. One is W2, second one is W prime, third one is W1 plus W prime prime, that is equal to PdV. Okay? And here there is a finite amount of work, so that means this is not zero. Okay, work is not zero. And from first law of thermodynamics tells us that du is equal to dq minus pdv. Okay, so that means we know that internal energy depends on temperature only for the ideal gas. Okay, U is the function of UT, and because there is no change in temperature from A to B or from C to D, that means in these two steps there is no change in internal energy. Okay, so that means for steps A, B and CD, which are isothermal processes, T is constant, that means U is constant, so this du would be 0. That means Q, the heat you supply, would be used to do the work. Okay, so Q2 is equal to W2. Likewise, here the heat you remove is at the cost of the internal energy, cost of work done on the system. That's W1. And we know that from our previous chapters, work done in an isothermal process is given by nRT natural log V2 over V1, and here Q1 is nRT log, let's, instead of writing V2 and V1, let's write, we're going from A to B, so VA VB. Here we're going from C to D, so CD. Okay, again this one is greater than 0, since we know that there is expansion, so since VB is greater than VA. Here this is less than 0 because it's a compressing step, so volume at D is less than volume at C. Okay. Now similarly, B and C are on same adiabat. Are on a same adiabat. That means the equation of state for an adiabatic process is PV gamma is equal to constant. So that means we can write this equation for A and B. Or before we write for A and B, let's express this in terms of temperature. So we also have the ideal gas equation, PV is equal to nRT. So we can write this in terms of pressure. Pressure is nRT over volume. So that means we can write our this adiabatic equation of state as P is nRT over V. V gamma is equal to constant. Okay, or N and R is constant, so we can incorporate this constant in this constant. So we have T V gamma minus 1 is equal to constant. Okay. Now we can write this for points B and C. Okay. So T at B, temperature is T2, volume is TB, and at C temperature is T1, volume is C. Okay. Likewise, points A and D are also on the same adiabat or adiabatic curve. Same adiabat AD. So we can write the equation of state for the adiabat as at D, at point D, temperature is T1, volume is VD gamma minus 1 is equal to temperature at A is T2, volume is VA gamma minus 1. So let's call this equation 1 and equation 2. So here we want to get rid of temperature. So we just want to show the relationship between volumes. So for that, what we can do is we can flip this. Okay, so T2 VA gamma minus 1 is equal to T1 VD gamma minus 1. Let's just call this 2. So divide equation 1 by equation 2 or equation 2 by equation 1. So divide 1 by 2. So what we get, T2 VB gamma minus 1 over T2 VA gamma minus 1 is equal to T1 VC gamma minus 1 over T1 VD gamma minus 1. So we can cancel T2 T2, T1 T1. So that will give us VB over VA gamma minus 1, VC over VD gamma minus 1. We can get rid of gamma minus 1 and gamma minus 1 on both sides. So that means we have VB over VA is equal to VC over VD. Okay, let's call this equation 3. Now we can take the ratio of Q1 and Q2. The reason we are doing all these things is to write this efficiency, which is 1 plus Q1 over Q2, this in terms of temperature. Okay, because it's often difficult to measure the heat involved in some process, but it's easier to measure temperature. That's why we want to express this in terms of temperature. So we want to get the ratio of Q1 and Q2, so let's get that. Now Q1 over Q2, so from our isothermal processes, we got Q1 to be nRT ln VB over VA, and Q2, no, that's Q1, Q2, so Q1 is VD, this is D over VC, and Q2 is nRT ln VB over VA. Okay, so we can cancel NR and NR. So for Q1, the starting temperature is T1. For Q2, here I should have written our initial temperature is T1 here and T2 here. Sorry, T2 here and T1 here. So this is 2. T1 over T2. So this one is ln VD over VC. VD over VC is a VA over VB, VA over VB over ln VB over VA. Okay. Now we can make the numerator and denominator same by pulling out a negative sign. Basically, if you have ln VA over VB, you can write this as ln VA minus VB, ln VB, and then you can pull negative sign out and write this as ln VB minus ln VA, and this is ln VB over VA. So you can flip the numerator and denominator inside ln by pulling negative sign out. So you can do that here. So T1 over T2 minus, let's say, 1 ln VB over VA ln VB over VA. So you can cancel these two terms, they are same. So Q1 over Q2 is equal to negative T1 over T2. Okay, with that, now we can write the efficiency of Carnot cycle is equal to 1 plus Q1 over Q2 is equal to 1 minus T1 over T2. Okay, so that's the efficiency of Carnot cycle for and ideal gas. And this is the maximum efficiency one can get from an heat engine. Okay, and again this is for ideal gas. If we use real gas, we get less efficiency that is less than the Carnot cycle. In the next chapter we'll show that no engine can have efficiency greater than Carnot cycle. Okay, so here one thing which is very important is the total work done in this whole process is equal to the area under this curve. Okay, so the area enclosed in this curve gives us the total work done in the whole process. So somehow if you want to find the total work given only this graphical representation, so basically you can find the area enveloped by the curves to find the total work.